As voice recognition technology has improved in recent years, I've become convinced that voice will be the user interface of the future. Why? When done well, voice wins over any other input method. Typing is the primary mechanism we use to interface with machines today. Yet, most English speakers type only about 40 words per minute. We can speak at about 3 times that rate, read at about 6 times that rate, and listen at 10 times that rate. We are moving to a world where we primarily speak to machines and read and listen to their responses. While state-of-the-art speech recognition systems perform reasonably well in close talking conditions, performance degrades in conditions where the microphone is far from the user. Imagine a common scenario in which one person is indoors speaking to an Amazon Echo. The audio captured by the Echo will be influenced by 1. The speaker's voice against the wall of the room. 2. The background noise from outside. 3. The acoustic echo coming from the device's loudspeaker. And 4. The output audio against the wall of the room. As the user moves further away from the product's microphones, the speech level decreases while the background noise level remains the same. Beyond noise and reverberation, other challenges include a lack of large-scale far-field data and unexplored efficient deep learning architectures. The bottom line is that there is still a huge gap between automatic speech recognition and human performance in these far-field scenarios. Speech recognition systems often use separate modules to perform speech recognition. The audio input is sent to an acoustic sensor, which converts acoustic signals to electronic, then to digital signals. Then it goes to a digital signal processing chip, where speech enhancement is applied with fixed embedded algorithms. These embedded algorithms perform traditional signal processing techniques, source localization, locating the direction of sound, and beamforming, suppressing background noise. The resulting enhanced signal goes to a conventional acoustic model for speech recognition. The drawback of fixed algorithms and components is that they cannot adapt to the rest of the trainable machine learning systems built on top of them. When you put a trainable deep learning system on a set of fixed chips, that deep learning model has to learn what the embedded algorithm is doing, undo it, and perform its own computation on top of it. This complicates things for far-field speech recognition because the audio input is already distorted, and along each step of converting the signal from acoustic to electric to digital, and then pre-processing, you lose information along the way. Google has been at the forefront of this research, demonstrating the use of raw waveforms as the output of the acoustic sensors, and thereby avoiding any pre-processing done by the built-in chips. That is, localization and beamforming of today's systems. In essence, Google is looking to combine steps 3 and 4 in the process. The idea is to give the microphone array more degrees of freedom to optimize the algorithms based on the data. Given that scope, an ideal hardware setup for any speech recognition application should do minimal digital signal processing in those fixed embedded chips. It should take in raw waveforms and build complicated deep learning algorithms on top that are both trainable and flexible. The question then becomes whether or not you can collect a lot of training data to train a deep learning algorithm for that specific hardware, or use other deep learning techniques to compensate for the differences in acoustic sensors. The problem today is that deep learning speech recognition models are trained on hundreds of thousands of hours of data that were collected on different hardware. Companies that build the infrastructure to gather, annotate, and train new models for data sets that don't exist yet will succeed. Ultimately, startups who are able to own the entire voice stack, both the data collection via the hardware and the trainable deep learning algorithm in the software, will be at a competitive advantage, providing better performance in speech recognition and language understanding.